Welcome back. Now, in this section, we are going to look at some of the advanced ideas about autocorrelation functions and what we call as linear response theory for the calculation of transport properties. So far what we have understood is there is molecular dynamic simulation, but then you can also come up with the equilibrium position by Monte Carlo simulation methods. We looked at the history of it, sampling distributions of different kind, importance sampling, and finally metropolis. And we said metropolis is really applicable for molecular dynamic simulations and understanding the properties of atoms in the equilibrium situation with the minimization algorithm. Then we looked at some of the application of that in order to use that as a precursor to molecular dynamic simulation, because molecular dynamics can take long time to come to the minimum configuration. However, now we are okay because Monte Carlo, by running let's say million sampling of the million of different kinds of locations of the particles and their configurations, we can find the one which we are looking for as a starting point for molecular dynamics. And with that understanding, we concluded the Monte Carlo simulation as a complementary technique with molecular dynamic simulations. Now, what we are going to look at is interatomic interactions, and we saw that and we revised that again, and we understood the last part that we did was first principle ab initio as well as electronic structure method, which was Carpernillo method, which is a very famous paper that you need to understand, and we went through it. We understood that there were certain approximation which is called density functional approximation by looking at the ground state electrical charge, and with that understanding we said Kuhn-Sham approximation with the single particle and Hohenberg and Kohn approximations. With those understanding, we were able to say that electronic structure based potential functions are more accurate. They provide us a lot more wealth of information. However, they are expensive in terms of computation, and they are also expensive in terms of the formulation, because they have lots of complication in terms of calculation of the terms. One of the things which we understood that Carpernillo were able to establish is that for minimization for the position of the atom, they use simulated annealing method, and that is where Monte Carlo can be used for simulated annealing. So, it is a kind of development from molecular dynamics, the interaction potential that really covers a lot of electronic structure in it, and then also understanding how you can calculate it using molecular dynamic simulations, primarily using Monte Carlo also as a method to use. And that is where the power of molecular dynamics has increased quite a bit, because now you are getting much more accurate description of the atomic forces. So, now we look at linear response theory for the transport coefficients. As I said in my previous section, transport coefficients are very important, primarily because they are the coefficient that define mobility of certain aspect of the system. So, if you look at, if you give a stress to a particular fluid system, you will see the ripples going through it, and those ripples have certain damping over a period of time, that is called fluctuation. And that is where this transport response theory also sometimes is called dissipation fluctuation theory, because it looks at the fluctuations and see how they dissipate over a period of time, and that gives very good idea about transport coefficient. So, if you are transporting a flux of properties, let us say flux of heat, and then if you provide a heat source on one side of the system, so heat flux is going through that particular system, and that heat flux, when it goes through, it has to follow a particular transport coefficient, which is called thermal conductivity, and that is inherent to the material property. Every material has a different thermal conductivity, and that is the transport coefficient, which is based on their electronic and atomic structure. So, this is where we look at how we are going to understand that the heat flux is going through a system of materials, and there could be composite material, and there will be different kinds of thermal conductivity between those composite elements. And so, understanding of the transport coefficient is important if you want to establish heat transfer phenomena. And as you know, heat transfer is used quite a bit in all kinds of applications, including your engines, including in boilers, including in any thermal systems. Even the system, those are based on the solar energy, where the radiation is converted into heat, and then heat is utilized in different ways to heat water and other substances. So, in all of that, main characteristic that you need to know in second order differential equation is, or diffusion equation as we call it, is the thermal conductivity. Similarly, if you are going to look at the fluid systems and the hydrodynamics of the fluid system, then you need to know the diffusion constant and viscosity of the fluid. So, if you look at Navier-Stokes equation, which comes from the second order differential again, and diffusion of the stress and strains and the fluid flow velocities and velocity variation as you go away from the boundary layers, then you understand that we need to have a coefficient which is viscous part of the hydrodynamic system, and that is where that becomes transport coefficient. The pressure is another element that allows you to move particles from one place to another. So, if you have a pressure difference, that will cause movement and mobility of the particles, and then you need to know how under that pressure condition the particle diffuse. So, most of the transport coefficient can be calculated using Green-Kubo formulation, and we will talk about what is Green-Kubo formulation, and that is where it is called linear response theory. And if you look at density correlation functions, as I talked about the pressures and how we change that. So, density correlation function is an example of important correlation function for diffusion. So, one is the time correlation function, where you looked at the velocity autocorrelation function earlier, where the time is very important and the frequency of motion and wavelengths are important for the vibrational property of a material. But now we are also looking at not that there is a vibration happening in the system, but also there is a mobility of the material through that system, where there is a diffusion taking place, and that is where you have to have space time correlation function. So, it is not only time, but also space. So, when you look at a space time correlation function, that becomes density correlation function. So, if you look at a density correlation function, which are also calculated using neutron scattering experiment and neutron inelastic observations and spectroscopy, that is where you can look at the density correlation functions, and response to that is also providing you a lot of information about the changes in the structure. So, you can then look at dynamic structure factor and also static structure factor, which connects back again to the experiments of diffraction patterns. So, if you have X-ray diffraction, and if you look at a material through an X-ray diffraction, then you will see locations of the particles, and those location of the particles and their mobility under different kinds of stress and strain condition can be predicted using structure factor. And so, the Fourier transform of the density correlation function becomes dynamic structure factor. So, if you look at G of R, which we looked at, which was radial distribution function, and if you take Fourier transform of radial distribution function, then what you have is static structure factor. So, we will see some of those calculations. We will do a calculation for a thin film of ice, which I had done long time back. So, you will understand using molecular dynamics how molecular dynamics can be applied for the Green-Kubo formulation, because these are all essentially correlation function starting from the self correlation, and that is what gives you diffusion constant, thermal conductivity, and other transport coefficient of different kind, which is very important, including some of the electrical transport coefficient, where you look at the voltage and the current and the resistivity, and how the charges can move through the system using the transport coefficient for electrical system. Thank you.